So in this one, we're going to walk through the definition of something called lattice energy. We're going to connect that to our periodic trends for ionization energy and electron affinity. And we're going to see exactly what's going on with how much energy is required to separate these things and if there's any stabilization going on. Now, when we're calculating lattice energy, it's going to be the enthalpy. We'll get a definition for that when we do thermochemistry, but it's going to be a specific kind of change of energy under standard states. That's what this degree sign looking thing, it's called the naught, what it's telling us. And lattice is just telling us that we're talking about a lattice energy. So lattice energy is the energy or enthalpy, either way you want to describe it right now, to separate 1 mole of ionic solid into gaseous ions. In other words, we're starting out with our neutral ionic species, and we're going to make it into the actual ions. So when it's ionically bound, they're not necessarily ions yet. It's when they separate that they become the ions. Now, there's going to be a 2-step process needed to do that. And you can see here I'm focusing on the 2 that are highlighted in more vivid colors. So the first thing we're going to do is we're going to pop those loose to be sodium atom in the gas phase and chlorine atom in the gas phase. And when I keep emphasizing atom, that means they're not charged yet. So there will be an energy associated with transferring 1 electron from the sodium over to the chlorine. So you can see here we end up having sodium atom turned into sodium ion. That should be stable. That's going to be an octet. Chlorine picked up 1 additional electron and became chloride. And I'm emphasizing the nomenclature here because it comes up later in this chapter. So sodium ion and chloride are going to be formed, and both of these are going to be gas phase. So there's a couple things happening here. There's going to be the energy needed to pop them loose from their neighbors, and then there's the energy needed to transfer the electron from one to the other. Lattice energy is going to tell us about how much energy was in that binding to the rest of the crystal lattice. Now, the small part of what we've got written down here is transferring our electron. Our ionization energy for sodium, it costs us some energy, but we know that sodium's able to do it. It's 496 kilojoules per mole. Not small, but not giant either. Now, our electron affinity for chlorine, how well it's able to grab that 1 electron and does it get stabilized? Well, yes, it got stabilized. We see that from the negative sign. It went from a high energy to a lower energy. That means it's more stable. So the negative sign is telling us it gained in stability. But even then, you can see, when we consider both these energies simultaneously, we still have to put in 147 kilojoules per mole from somewhere else in order to make this process happen. Now, that's not that big of an energy difference, surprisingly enough. But it still does cost us energy. Now, the thing that throws people on this is, why are we being so picky about solid to gas phase in this definition? Well, keep in mind, when you drop salt into water, sodium chloride, what happens? It dissolves, and it dissolves really easily and really well, and it dissolves spontaneously. But what we're talking about is the same sort of a process here. We're getting the sodium and the chlorine to come apart, become sodium and chloride ion, but instead of being in the gas phase, they're surrounded by water molecules that are helping them stay separated from everything else. We're saying, great, we know the water helps and that can make it do things that we wouldn't be able to do when they're by themselves. So we're going to focus on when they're by themselves. So if we take away any assistance, in other words, in the gas phase where there's no molecule close enough to do anything with them, that's the kind of thing we're talking about here. So we're talking about, great, we'll have a solid. This is when they're sitting there by themselves. Nothing is helping them stay together. We're going to pop them apart with nothing helping them to stay apart. How much energy is required to actually pull these 2 apart? So what we're really describing is how much energy is required to take these apart so that they're completely separated from each other, when that energy is the only thing helping. Well, the amount of energy we have to stick in there to do that is pretty big. We have to stick in 787 kilojoules per mole in order to do that. Now, there's a big difference between that. So why would this be a spontaneous possible process? Well, it turns out in water, you're having enough extra help from the water molecules to pay for it. But if you don't, that table salt is going to stay together pretty much forever. It costs 800 kilojoules per mole to pull those 2 apart. That's insane. That's a lot of energy. Now, it's not the biggest energy we'll talk about, but it's a big one. So these things are not going to spontaneously separate. They're also going to be held very rigidly because there's no wiggle room. These things aren't accidentally popping loose into the gas phase. They're staying attached and moored very tightly to each other. That's one of the reasons that we'll see lots of properties that come from crystal lattices. Now, lattice energy is typically going to be big if you have bigger charges. It's typically going to be small for bigger internuclear distances because basically, even if you've got big charges, if you already start with them partially separated in space, it's easier to pop them apart. And when they're big, like that, they can't really come as close together in the first place to actually stick tightly. So when they're small, big lattice energy. When they have big charges, big lattice energy. As you increase those two things, it becomes very hard to separate them from each other.